So the second talk is probabilistic analysis of time-sensitive systems. And so the problem here is that we have large, complex systems. We talked about these multi-core systems where we have multiple cores, and we might have difficulty verifying correctness of them because of properties like caching and so forth can make predictable real-time very difficult. So we want to develop techniques that will allow us to vary correctness of the systems. And one of the problems that these systems tend to be very large and complex, and even though there are formal methods, these systems are too complex to use these formal methods. And so we're using a technique based on something called statistical model checking, which is a simulation-based technique for verifying correctness. And so sort of in a nutshell, statistical model checking takes some system that takes some random inputs. We're operating in a random environment, some probabilistic temporal logic formula that we want to verify, and it gives us a probability that that property holds. And this property is often a failure property. We want to know the probability that some random input is going to cause the system to fail. And we want to know with some confidence interval, which we can sort of quantify with a relative error value. Basically, it's sort of a Monte Carlo-based technique. And just to define relative error, that's the standard deviation divided by the mean. So a measure of obviously the more simulations I do, the lower my relative error is going to be. So sort of at a basic level, statistical model checking is very simple and straightforward. I have, so if you look at that upper graph, I have some input space where I have some probability distribution over that input space. I generate a bunch of random samples. Some of the samples are going to land in the fault region. That sort of red jaggy area is the fault region. So in that case, one of my 10 samples fell in the fault region. So it's very straightforward to calculate the probability of a fault is going to be 1 over the total number of samples, and then I can calculate relative error from the standard deviation. Just as a notation-wise, that sort of I of x notation is something we call an indicator function. So we throw in the input values, and it gives us a 1 if the property holds, a 0 if the property doesn't hold. Now, the problem with that is it's basically the source code of the program. So it's not something we could analyze straightforward, directly mathematically. Now, people have used a technique called importance sampling to sort of speed up, reduce the number of simulations that I need to get an accurate result. And the basic idea of importance sampling is to shift the probability space, change the input distribution, change the parameters of the input distribution to move the probability density in such a way that I get more samples in the fault region and then map that back to the original distribution. So when you do that, you need to use a weighting function to weight each of the samples that fall in the fault region. And in this case, we got the 0.2, the 0.5, the 0.3. We still end up with the same probability incident with a much more lower relative error. Now, one of the problems with this approach is that software is often very complex. There are often multiple paths to a fault region, multiple spots in the input space. And it's very difficult by just shifting the probability around with the distribution parameters to handle these types of problems. So, okay. Something got formatted. Okay, so we've developed this code we call Osmosis, which uses a technique called semantic importance sampling. And so this is a way of analyzing the source code to create what we call an abstract indicator function that allows us to do the simulation much faster. So the input model is basically a specification in C. You can imagine that there's several assert statements in there. We give it the input distributions, and we want to calculate the probability that one of the assertions does not hold. So the basic approach is to build what we call an abstract indicator function, that I star, that's an over-approximation of the fault region. We use what's called an SMC solver called DReal, which is developed on campus that can tell us whether some logic formula is satisfied or dissatisfied. That's sort of the core of that. So overall, the osmosis main algorithm is that we generate the approximation of the fault region. So say that sort of red jaggy area is our fault. The sort of the gray box is our entire input space. And that sort of green box might be our abstraction of the input space. So remember the jaggy square is just sort of the program itself, but the green box is a simple enough representation that we can deal with that analytically. So once we have that abstract indicator function, we move on to the stochastic statistical model checking phase. We generate random samples, but we only generate them in the abstract indicator function because we know that there's no fault region outside that area. And once we've done that, we create an initial raw estimate, probability estimate. That's the number of samples that fall in the fault region over the total number of samples. And then we need to calculate a scale factor as sort of the fraction of the probability space that I star covers compared to the total in space, and we call that P star. And then the final probability estimate is just going to be the product of those two, the scale factor and the simulation result from within the I star region. And we've also shown that the relative error doesn't change. So whatever relative error we get on the P raw estimation is the same relative error that you would get from the estimate for the problem that you're interested in. So here's how the abstract indicator function generation works. So let's say we have two random inputs, A and B. So we look at a quantile space breakdown, basically the CDF of the two input variables. And suppose we have two fault regions. So first we create a logic formula from the C specification, and we send that to the DReal engine. And it will tell us either SAT, that there is a fault in that region, or unsat, if there is not a fault in the region. So we start out giving the full region. It says, yes, there's a fault somewhere in there. So now we can divide that in two and recursively call DReal on the two halves. So it's going to say SAT on both halves. And then we break those down in two. We're going to get unsat on those two halves. Once we get an unsat, we're done with that. We don't need to recurse further on that. We only recurse when you get a SAT. And so you keep going, you break this down, you get a set of those small green cubes which represent the over approximation of the fault region. Okay, so I'm going to give some examples from a small model problem. So imagine we have an air hockey table, we have a puck, we have some red target. Our random inputs, we're going to give a strike it at a random angle at a force that will send it some random distance, and it's going to go around, it's going to bounce around, come to a stop somewhere. If it doesn't hit the target, we're going to say that's okay. If it bounces around and it lands on a target, we're going to say that's not okay. And so you can see that there's lots of different paths that the puck can potentially take, lots of different regions in the input space that can lead you to a fault. And so we want to be able to speed up the simulation that can find us there. So here's sort of what we call a fault map that shows where in the input space the fault occurs. So on the bottom axis, that's the CDF of the angle. The vertical axis is the CDF of the distance. And I don't know if you can see well, the small red dots are the actual fault area. So the green boxes around them, that's the abstract indicator function that we generated with our technique. And so when we're doing the simulation, we're only simulating within the green boxes there. So we look at what kind of speed up we get. So this is looking at the recursion depth. As we recurse down with the abstract indicator function, we have a set of depth limit, how deep we want to go. Obviously, the deeper we go, the more accurate our abstract indicator function is going to be. So we should get more speed up with a deeper simulation. And with a simulation depth of 1, that's basically the same as doing nothing. We're doing pure Monte Carlo simulation. And so we can see that when we set a target relative error, so the relative error of all these estimates is the same, we can see we get about a 2-order magnitude reduction in the number of samples required to achieve that same relative error. Also, it's interesting to look at remember that scale factor. The P star is in some essence an over-approximation of the probability value. So as we increase the depth, that P star is going to decrease, and it's going to approach the actual fault probability for the problem. Okay, so we also looked at a couple optimizations, sort of in the generation of the abstract indicator function. Sort of a lot of the time is in the execution of DReal, the SAT solver on the problem. So we'd like to do all we can to reduce the number of calls as much as possible. And so we looked at sort of two optimization approaches. In one optimization approach, sort of if our parent call returns SAT, and then we're looking at the two child calls, if the first child call is unsat, then we know that the second half has to be satisfiable. And so we can skip our call to DReal and assume that's satisfiable, because the parent says somewhere in that big box is a fault. And we know that the left half doesn't have a fault, so the right half has to have a fault. So that's one optimization. The other optimization we can make is based on the counterexample. The SAT solver will give you a single counterexample of a fault. So if the parent call, we make that parent call, that red dot is where it generates the counterexample. Whichever child side that counterexample falls in, we can skip that call to the SAT solver and assume SAT on that side, and then call DReal on the other side as usual. So if we look at sort of what kind of speed up or what kind of reduction in the number of calls to the solver we get, so the top curve is using no optimization effects. The next curve down is when we use the optimization 1. The bottom curve is when we use optimization 2. And there's just below that, there's another small curve just slightly low when we use the two optimizations together. So what we found out was that actually optimization 2 is the most effective, and optimization 1 will give you a small improvement on top of that. Right, so in conclusion, so we've developed this technique called semantic importance sampling, which is based on creating an over-approximation of the fault region, which allows us to create this alternate input distribution to speed up the simulation time. You can tune sort of the level by the recursion depth. You can tune how deep you want to go, and reduce the SMC time, the statistical model checking time, by multiple orders of magnitude. We've developed this in this tool called Osmosis, which takes C-like input and uses the DReal engine to generate these approximate models. And so it's very useful when you have multiple fault regions in your input space. And again, we've developed these optimization techniques that so far we've been able to reduce the number of calls to the solver by half. Thank you.